Hello everyone, welcome back to Calculus. This time we are continuing to work on derivatives, and to be precise, it's the applications of derivatives. So in this section, 4.7, we are working on some word problems, or formally speaking, optimization problems. Well, this is kind of my general understanding. A lot of times someone just think math, that's all about numbers. But anyway, I really want to know, well, math, certainly we deal with numbers, a lot of numbers. And it does require a lot of reading and writing. So putting a simple way to solve a word problem, really, literally, you will have to read those words carefully. Make sure you do understand the situation, and then you want to convert the word problem into a math problem, and then solve the math problem, and then provide the answer to the actual situation, not just only about numbers. Certainly, numbers are important, or really are very important. Okay, so this is what I copied the list of steps or general ideas how to solve those word problems or application problems, or, well, really, as for according to the textbook, the problem solving strategy and how to solve optimization problems. Step one, you want to introduce all variables. And I still want to say, before you get to step one, you really needed to read the problem very carefully. Make sure you do understand the situation, and then you want to use mathematical notations or introduce all variables. And it is very helpful. Many times you want to draw a figure, or maybe draw multiple figures, graphs, okay. And then, we'll mark out, label the information, okay, the length, the width, or any quantity, useful quantity, related important quantity on the graph. And then certainly, step two, you will have to determine which quantity is to be maximized or minimized. Actually, I should have mentioned earlier, an optimization problem usually involves with the maximum or minimum of certain quantities. Because many times it is just true, the best solution, it is a maximum or minimum. Like if you run a business, well, I guess the optimized way to run a business, it is to maximize your profit. So that's a maximum. And on the other side, another way to run a business successfully or in an optimized way, you want to reduce the cost. So on the other side, in order to make maximum profit, and you really want to minimize your cost. So an optimized problem usually it is about mathematically it is about to find out a maximum or minimum. So you do need to, after reading the problem, you do need to understand clearly which quantity, which variable to maximize or minimize. And then the maximum problems, minimum problems, basically you're going to have some conditions or requirements in words. And then those conditions or requirements will change into equations or functions. Will change into equations and the functions. Okay. And step four, write any equations relating to independent variable in the formula from step three. And basically, so far you really want to understand the maximum or minimum we can handle. So far, we only really can handle situation, the maximum or minimum for a function of one single variable. So those word problems, and similarly, they may involve with multiple quantities, multiple variables, multiple notations. But anyway, eventually you will have to convert those functions into a function of a single variable, into a function of a single variable. And also, step five, well, when you have functions, usually you understand that, well, for functions, there's a domain and a range. Domain, it is the possible all x values, the possible x values. That's a domain of the function. And also, because those word problems for certain kind of actual situations. Okay, so usually there's additional, besides the domain, the mathematical requirement, the domain of the function, and also there are some restrictions from the actual situation. So be aware of the situation and do not just solve the problem mathematically. After you get in the answer, you want to see if really your number would match, would fit the actual situation. And then number 6, well, about maximums and the minimums, and usually you need to calculate derivatives. And remember, the maximums and the derivatives usually will occur at a critical point. A critical point, it is a point where the derivative is 0 or derivative is not defined. So usually the maximum or minimum will occur at a critical point. These are the steps listed on the textbook. Again, as I'm saying, when you actually solve the problem, you really don't necessarily just follow in those 6 steps, okay? And even for me, I really don't follow those steps well all the time. But anyway, hopefully you see the idea. Okay, in general, as I'm saying, my understanding, this is the way how I treat a word problem or application problem or the optimization problem. You really need to read the requirements carefully and make sure you understand the situation in a mathematical way. And then you want to convert the actual problem into a mathematical problem. And then solve the mathematical problem, and then finally make a statement just to say how your number will fit for the situation. Step 1, 2, 3, 4, 5, 6. Okay, you don't need to necessarily follow those steps precisely, but anyway, those steps, they do cover the general idea as I just stated. And so I'm thinking to do some examples. How about let's just move quickly the first example. It's on the textbook. I hope this would be easy enough for me to explain. It is to maximize an area. And the task, it is very simple. We are considering to build a rectangular garden. But anyway, the rectangular garden, a piece of lot, a piece of land. One side of the rectangular garden, it is built using the stones. It's a rock wall. It's a rock wall. So you really don't need to consider about any fencing at all along the wall, along the side with the stone wall here, okay, along the rock wall here. And then, well, what you need to consider here is to claim this as your property, and you want to put a fence all around, and it will have to be in a rectangular shape. But anyway, there's one thing. The total fencing material you may have, it is 100 feet. And then what you need to consider here is you want to find out the way to claim your piece of land, okay, a piece of land such that it has a maximum area. And also you take advantage of the total amount of fencing material. And also, as I said, before I move to the steps, I really want you to know, you really want to think about this carefully if you really understand the situation. I'm saying, given this amount of fencing material, you could build a rectangular garden claim piece of land in different ways. Okay. Because I'm doing this entire thing on the screen, it's a little harder for me to do actual drawings. As I'm saying, you may want to pause a little bit. Make sure you can show at least there are 3 different ways. And in each way, indeed, you will see the area included will be different. So it makes sense to me. Certainly it's somewhat maybe a little tricky thing to find out the area with the maximum there, okay. All right, let's get to the point if we can solve this. Step one. First of all, as I'm saying, I understand that there are many different ways to build this rectangular garden. As long as one side it is a rock wall, okay, against the rock wall. Say the rock wall it is already there, and it doesn't matter how long or how short you want to build, have your garden against it. And then we need to have 3 sides to use the fencing material. So I said simply x, it is the length of the rectangular garden, and then y, it is the width. Okay. And then, as I just said, well, we do have 6 steps, but anyway, I hope you do understand on the idea. You really don't necessarily follow those steps one by one. As long as you have your idea clear, you really can solve the same problem or a different problem in just in different ways. That's all I can tell, really. But anyway, the general idea it is there. So step 1, I think it doesn't match. And then I think step 2 and 3, somewhat I tried to have step and step 3 together. Because the quantity we need to maximize, it is clear. It is the area. And then if you say maximize the area, I'm saying there are many different ways, right? What do you mean by the maximize the area? The area, it is in the rectangular shape. So certainly the area, it is determined by x and y. And again, if you look at this product, I hope you see there are really different arrangements. Okay. And then step 4, somewhat it is very important. If according to step 2 and 3, if that's the objective, if we only consider the objective as I'm saying, hopefully you see that too. There are many different ways. And then step 4, it is the constraint, or it is the requirement, because we cannot use any amount of material, okay? The total fencing material, it is just given. And hopefully it should be easier to understand. If you use more material, you're going to have more land, possibly more area covered. So as I'm saying, you really want to use all the fencing material. So I use x to denote the length and y to the width for this rectangular land. And then the total fencing material I need here, okay, because the side opposite to x, it is against the stone. And then I have 2 other sides. So the total fencing material I need here, it is x plus 2y, which is 100 foot. And that's all we are provided. We cannot do 101. And certainly, I guess you don't want to do 99. Let's use all the fencing material. Hopefully, we could cover as much area as possible. Okay. And then at this point, as I'm saying, you go back, look at what I stated as the objective. It is to maximize the area. Area, it is calculated using x and y, right? So there are many different ways. And what we can consider here is the area, it is a function of 2 variables at this moment. We cannot do that. So you want to do some work to make sure the area is a function of a single variable. So according to the condition, the constraint, as I just stated, I know x can be solved from this equation. We solve for x is y, sorry, I have to make this correction. Y can be replaced with x. Y is 100 minus x over 2. And also make sure you do understand, we are having the fencing material, so x and y clearly will have to be both positive. Whatever the numbers you get will have to be positive. And clearly, I guess, either x or y cannot go beyond 100 or cannot even go 50, really. Well, 50 is possible. 50 is possible. Anyway, at least the x or y cannot go beyond 100. Okay. And then step 6, finally we reach to the point. We do have a mathematical function, area, in terms of x only. It is x times y, so y it is replaced with the formula we just derived in step 4. And indeed, area, it is a function of x. And then we calculated the derivative a prime, and then I figured out actually there's one critical point, x equals 50. 50 it is a critical point. 50 it is a critical point, okay. And then somewhat I don't want to make this thing too long because the application problem does require a lot of work. And then I really want to know here is somewhat I skipped some work. Basically, remember at a critical point, it could be a maximum, could be minimum. How do we know it has to be a maximum? So I said that from the first derivative test, you really want to give a try, double check if you're convinced if it really makes sense. Indeed, using the first derivative test, we can tell this critical point, indeed, it is a maximum. Okay, so when x equals 50, and then accordingly from the formula we derived earlier, y turns out to be 25. And indeed, in this case, we are very confident to say the maximum area it is reached, which is 1,250 square feet. And it is achieved when you choose x as 50 and y as 25. So I suppose this is a very simple situation to solve an optimization problem. It is to find out the maximum area. Thank you for watching.